Nothing beats continuing with more derivative rules. In this video, we are going to figure out what the derivative of the natural exponential function is. So let's get going here. Okay, so that is, we want to find this derivative right here. The derivative with respect to x of the function e to the x, where e, of course, is Euler's number, approximately 2.71 if you recur. So that is going to be our goal in this video. Figure that out. And just as a reminder, remember, here's what the graph of e to the x looks like. Right there, that exponential growth. So when looking at this graph, it's nice and smooth. It's always increasing. So we should expect that the derivative of this function e to the x is going to be differential, or the derivative, that is, will be existing for all values of x. And it should also be positive, right? Because it's always increasing function. All right, so to get going here, figure out how all this works, we're going to first just consider a general exponential function. Say f of x is b to the x, where, of course, b is assumed to be positive and b is not equal to 1. So that's how we define an exponential function in general. So we're going to consider that. Okay, because if b is equal to e, then we will get, of course, the function of consideration. So just applying the definition of the derivative, here's what we start with. All right, derivative of an exponential function b to the x, by definition, limit as h goes to 0 of f of x plus h minus f of x divided by h. And of course, our f of x here, remember, is just the general exponential function b to the x. And therefore, we get this limit statement right there. Limit as h goes to 0 of b to the x plus h minus b to the x divided by h. And as is the case with all of the other derivatives that we've been investigating, this, as h goes to 0, goes to 0 divided by 0, indeterminate form. And as usual, we got more things to do here to figure out what that limit is. So what do we do? Well, in this statement right here, just notice that when we have that limit of consideration right above, the h is the variable that is changing within the limit, right? Hence the limit as h is going to 0. So that term with b to the x in it, in fact, there's going to be two parts here that have b to the x, that's going to behave like a constant within the limit because x is not the variable that's changing within the limit, it's the h that's changing. So for that reason, we can rewrite the limit of investigation as follows. Okay, here's our limit that we're at. And then I went ahead and just rewrote this next step right here as b to the x times b to the h minus b to the x divided by h within the limit. In other words, I'm just using properties of exponents to rewrite b to the x plus h as b to the x times b to the h. And again, because b to the x is acting like a constant within the limit, then by constant multiplier rule for limits, assuming this limit exists, of course, we can take the b to the x out in front, right? Again, because that is behaving like a constant within the limit. So I can rewrite this limit as b to the x times the limit as h goes to 0 of b to the h minus 1 over h. So all of that is the derivative of the exponential function b to the x, right? That's what this is. Just rewriting it in this form right there. Now you say, well, it still goes to 0 over 0 as h goes to 0, so how is that really going to help us? Well, that limit statement right there is going to really help us identify something specifically. Notice, if x is 0, okay, within that limit, then what happens? Well, we should take notice of this. If x is 0 and say I want to evaluate my derivative of b to the x at x is 0, then by definition, that's going to be the limit as h goes to 0 of f of 0 plus h minus f of 0 divided by h. And since our function, of course, is b to the x, then we get this statement right here. limit as h goes to 0 of b to the 0 plus h minus b to the 0 divided by h. And what are we left with? Well, b to the 0 is 1, and b to the 0 plus h is just b to the h, so it's the same as limit as h goes to 0 of b to the h minus 1 over h. You go, okay, well, that's great, but remember, we saw that limit right there, right? And we just show that that limit is really the derivative of the exponential function b to the x when x is 0. And thus, from this derivation that we just figured out, it follows that because the derivative of b to the x is the function b to the x times this limit right there, and that limit is exactly the same as the derivative of the function at 0, then it allows us to conclude that, oh, well, look at that. For any exponential function, the derivative of the exponential function is the function itself, b to the x, times the derivative of that function at 0, assuming, of course, here f of x is equal to b to the x. So that's kind of interesting in that exponential functions have the property such that their rates of change are always the derivative of the function itself at 0 times the function itself. So it's really a constant multiple of itself. So it still doesn't solve the problem that we're after yet, right? We're after the derivative of the natural exponential function e to the x, but it's going to help us, as we're going to see. So here's just a nice picture showing, oh, look, there's a general exponential function b to the x. I just drew a growth situation, but of course we can have decay as well. And you see the tangent line at 0, whatever the slope of that tangent line is going to be the derivative of the function at 0. And so once I figure out what that is and I multiply it with the original function, I'll have my derivative function for all values of x. So to help us get a little further here, we are going to consider three functions. G of x, let's say, is 2 to the x. F of x is our friend here, e to the x. And h of x is 3 to the x. Now remember, e is approximately 2.71. It's an irrational number, but it's approximately equal to that. And thus, obviously, it follows that right down here, this statement, e is bigger than 2, but it's less than 3, right? And then if I consider the graphs of these functions, here, the red graph, g of x is 2 to the x. The blue graph, f of x is e to the x. And the green graph, h of x is 3 to the x. So because the bases here, 2, e, and 3, are satisfying the inequality, 2 is less than e is less than 3, then, you know, if we have a growth situation for an exponential function, the bigger the base, the faster that it will increase. And that's all consistent with our picture here, right? 3 to the x is increasing the fastest, e to the x is between the two functions, and 2 to the x is increasing the slowest of the three. So why am I saying that? Well, because if we then go look at the tangent line at x is 0, in other words, finding the slopes of these three different functions above at x is 0, then we should expect that the slope at 0 for 2 to the x is less than the slope of the function e to the x at 0, and that should be less than the slope of the function 3 to the x at 0 because of the reasons above. So maybe we can try to figure out what these values are approximately by investigating the derivative values right above. And I notice here there's a typo, investigate. Investigate, not investigage. I don't know if investigage is a word or not, but clearly that's not what I meant. Okay, so here's the table of values. So again, remember, the derivatives of these functions at 0 are given by, remember, the derivative with respect to x of any exponential function b to the x at x is 0 is always going to be the limit as h goes to 0 of b to the h minus 1 over h. And so if I just replace b there with 2, or I replace b with 3, then I get the corresponding derivatives that I'm after. This one right here, right, that column is showing the derivative with respect to x of 2 to the x at x is 0. And then this right here is showing the derivative with respect to x of 3 to the x at x is 0. Right? And how is that being shown? Well, I'm just looking at the quotient within my limit, and then I'm letting h values get tinier and tinier and tinier closer to 0. So this can be verified just by plugging in these various values of h. And as we see, as h gets very, very tiny, it seems to be that the derivative of 2 to the x at 0 is about 0.6934, and the derivative of 3 to the x at x is 0 is approximately 1.0992. So what is that going to tell us then about e to the x at 0? Well, like I just said, it seems to indicate these two things right here. Derivative of 2 to the x at 0 and derivative of 3 to the x at 0 is approximately these numbers here, say 0.693 just rounding and 1.09 just rounding. And we already stated, remember, that the derivative of e to the x should be trapped in between these two things because of the previous discussion we just had. So it should follow then that, like I just said, the derivative of e to the x at x is equal to 0 should be trapped in between these two values. And in fact, we might even conjecture or hypothesize that the derivative with respect to x of e to the x at x is equal to 0, maybe it's actually 1. Notice that 1 is trapped in between those two numbers. That would be pretty nice. And in fact, that is our conjecture here. That is, the derivative with respect to x of e to the x at x is 0, which, of course, right here is our limit as h goes to 0 of e to the h minus 1 over h, that is equal to 1. Okay? That is our hypothesis. We're going to prove it here in a moment. And if you go and look around, e is a very special number, and sometimes it is defined as the number such that this limit is actually true. But we can actually show it to be true. And to do that, you got to kind of recall some things from usually a pre-calculus topic when you look at finance mathematics, and that is these two limits. Now, you may have forgotten these limits. That's okay. But these limits are true. And that is the limit as x goes to infinity of 1 plus 1 over x all to the x power is actually equal to e. And moreover, the second one, the limit as x goes to 0 of 1 plus x quantity to the 1 over x power is also equal to e. So these are usually talked about when you look at compound interest formulas, specifically continuously compounded interest, when you study that in a pre-calculus setting. So just recall those, because if we say, okay, those are true, then we're going to be able to show exactly what we want to show. By making a substitution, let's just let e to the h minus 1 be equal to, say, u. And that follows then, if I just add 1 to both sides, that e to the h is u plus 1. And then if I solve that for h by taking the natural logarithm of both sides, I get that h is the natural log of u plus 1. Okay? So notice, as h goes to 0, then u is also going to 0. How so? Well, just look at that statement right there. As h goes to 0, right, then e to the h goes to 1, and hence 1 minus 1 is 0, so u will also go to 0. So I'm going to use those substitutions to rewrite my limit that we're investigating, right? This limit right here, limit as h goes to 0 of e to the h minus 1 divided by h. So the numerator, e to the h minus 1, that's what we are calling u, remember, right up here. So hence the u. And then, remember, we solve for h right there. So that's in our denominator. same as natural log of u plus 1. And remember, as h goes to 0, u also goes to 0. So this limit is the same as this right here. And then I'll just rewrite it using a little bit of algebra. And that is this statement right there, limit as u goes to 0 now of 1 divided by u times natural log of u plus 1, right? 1 over u is u. So I'm just taking that u in the numerator and dividing by its reciprocal in the denominator, which gives us the exact same thing. Now, why does that help? Because then if I apply properties of logarithms in this step right here, right, remember that if I have a logarithm and I have, say, constant times natural log of x, for instance, well, that is the exact same thing as the natural log of x to that constant. That's a property not just for natural logs, but for all logarithms. And so that's why you see this 1 over u now appearing as the exponent on the input value u plus 1. But remember that as u goes to 0 there, go back up here real quick. Remember this statement right there. Limit as the input x goes to 0 of 1 plus x to the 1 over x power is e. And exactly that's our limit right here that we're seeing in the denominator. So as u goes to 0, this entire thing, right, is going to go to the natural log of e, since u plus 1 to the 1 over u power goes to e. And hence 1 divided by natural log of e is 1. And that indeed proves that the limit as h goes to 0 of e to the h minus 1 over h is equal to 1. What does that finally give us? That the derivative of e to the x with respect to x is e to the x. Why? Well, remember, the derivative with respect to x of an exponential function b to the x is going to be equal to the function b to the x times that same function's derivative at 0. But we just showed right above, right, that the derivative with respect to x of e to the x at x is equal to 0 is equal to 1. And so if b, our base, is e, then we just get e to the x times 1, which of course is e to the x. So quite amazingly, this is a very special function, because other than a constant function that equals 0, this is a function that has a derivative equal to itself. So derivative of e to the x is e to the x when differentiating with respect to x. So we did it. We figured it out. Now, this doesn't show, of course, what the general derivative is of an exponential function b to the x, but that'll come later. Right now, we're just focusing on some initial rules, of course, in this section, and this is another initial rule that you can add to your list of rules. So now that we have concluded that, we're going to conclude the video with an example. And here we are going to be given this function f of x is 2e to the x minus 6x, okay? First thing we want to do in part A is find all the points on the graph of the function f where the tangent line is horizontal. So what is that really meaning? We want to figure out which values of x give us that the derivative of this function with respect to x is equal to 0. Because if you have a horizontal tangent line, of course, that slope of that line is 0. So in order to do that, we'll have to find the derivative. So let's find the derivative. All right, well, derivative with respect to x of 2e to the x minus 6x. We can use our sum and difference rules for derivatives. So this is the same as 2 times the derivative with respect to x of e to the x. So notice I also use the constant multiplier rule there. And then minus a 6 times the derivative with respect to x of x. And now that we've figured out that the derivative of e to the x with respect to x is itself, this gives us 2e to the x minus a 6, technically times a 1, since the derivative of x is just 1. So there's our derivative in general. All right. Now we want to figure out where that equals 0 so that we can know the x locations for which the function has a horizontal tangent line. And so just solving this, we get 2e to the x is equal to 6, which is the same thing as e to the x is equal to 3. And just solving that, we get that x is equal to the natural log of 3. Okay, so there's the x location. I guess it's just one location here, right, for which that function f of x has a horizontal tangent line. And just be careful because it says find all points. So usually when we talk about points, we refer to that as an ordered pair. Now we found the x value, but what's the y value? Well, we just go ahead and plug that x that we just found into our function to get the corresponding output there. So what is f of the natural log of 3? Well, just plug it in. 2e to the natural log of 3 minus 6 times the natural log of 3. E to the natural log of 3 is 3 by inverse properties. So this is 2 times 3 minus 6 times the natural log of 3, which is 6 minus 6 times the natural log of 3, or if you prefer, 6 times 1 minus the natural log of 3 if I just factor out the 6. Thus, the point for which this happens is the ordered pair natural log of 3, comma, 6 minus 6 natural log of 3. I'm just writing it in that other form. And there we have it. So there's part A. We figured out the point on the graph, ended up being only one point, for which the function f of x has a horizontal tangent line. And of course, we're doing this example now because we have the derivative of e to the x. Now it says in part B, find the equation of the tangent line to the function f at the location x is equal to the natural log of 8 here. So all we're going to do is find the slope of that tangent line by plugging natural log of 8 into our derivative function. And then we will use the equation of a line to figure that out. So we will need the output of the function at ln 8, right? So what is f of ln 8 first of all? Well, remember our function up here is 2e to the x minus 6x, so I'll plug it in. 2 times e to the natural log of 8 minus 6 times the natural log of 8. E to the natural log of 8 is 8. 8 times 2 is 16, so you get 16 minus 6 times natural log of 8. So the point on the graph, right, the point of tangency, if you will, is the ordered pair natural log of 8, comma, 16 minus 6 times the natural log of 8. So we need that point to find the equation of the tangent line, but we also need the slope of that tangent line. So that's where we're going to go and plug in our natural log of 8 into our derivative. Remember that the derivative function here, f prime of x, we found out that that was going to be equal to 2e to the x minus 6. Thus, plug in natural log of 8. F prime of the natural log of 8 here is going to be 2 times e to the natural log of 8, and then minus a 6, which is the same as 16 minus 6, which is 10. So there's our slope, and thus we can find the equation of the tangent line of this function. Let's use our point slope form. We're going to get y minus the output value, which was, remember, 16 minus 6 times the natural log of 8, is equal to our slope, 10 times x minus that input location, the natural log of 8. So I guess we could choose to leave it in point slope form, but why not just isolate the y as one last step by adding this quantity to both sides? And we're going to get that y is equal to, add that to both sides, a 16 minus a 6 natural log of 8 plus a 10x minus a 10 times the natural log of 8. And you see we have a couple like terms here. And finally we get, excuse me, y is equal to, let's write it as 10x, and then plus a 16, and then minus a 16 times the natural log of 8. There's our equation of the tangent line in slope-intercept form, and we did it. So that is the end of the video. We derived what the derivative of e to the x was in this video, and then we did an example using that result. Many more videos to come on derivatives. The next one is going to be investigating higher order derivatives. So like when we take derivatives of derivatives, slopes of slopes and whatnot. So we'll check that out in the next video. But that's it for this one. This is Math and Beats, and I'm out of here.